going to look at implicit differentiation with related rates. We've talked about implicit differentiation so far with respect to equations such as this. This is an equation where I could actually look at the graph of it. For this particular one, the graph would be a circle. And when I find the derivative, that derivative would represent slope of tangent lines to this circle. Well, we're going to be getting away from equations where I could look at the graph of it. So for instance, I'm not going to be graphing them on the XY axis anymore. And we're going to be looking at formulas. It's going to be formulas that represent something that we know. So for instance, here's a formula, and it's representing the volume of a cylinder. I'll still have a graph, but I'm not going to graph it on the XY axis. I'm going to have a diagram, really. So this is the formula for volume of a cylinder. And if I looked at the derivative would be representing the rate of change of some aspect of the cylinder. Now, usually this change is going to be with respect to time. So we're going to see that part of our notation for derivatives isn't going to be with respect to x anymore. It's going to be with respect to time, and therefore the bottom, it's not really a fraction, although it feels that way, the bottom of our derivative is going to be dt. What are some aspects that change in the volume formula for a cylinder? Well, the volume of the cylinder can change. Maybe you're pouring some water into this. Maybe this is a can of soup, and the volume in the item is changing. Well, this would represent how it's changing, how the volume is changing. So our derivatives now are about rates of change rather than only thinking about them as slopes of a tangent line. We'll be able to talk about one specific moment in time, and so now we're back to that idea of an instantaneous rate of change. Well, if I look at this formula, though, there's a lot of other variables in it. For instance, the radius. If I want to talk about the radius as rate of change, the variable that would represent that would be dr dt. What do you think the variable would be to represent the height's rate of change? It would be dh dt. Well, if I'm talking about a rate of change equation, that is about the derivative. And so we're going to be taking the derivative on formulas now, not just things like equations of x squared plus y squared equals 10. We'll be taking the derivative of a formula. And that formula might allow all the variables to change, which means I would see dv dt, dr dt, dh dt. But the formula might have a scenario where some aspects of it are not changing. For instance, in this cylinder, it would be really common for the radius to be the same whether I have practically nothing about halfway up or a completely full cylinder. The radius isn't changing. So what we're going to look at is what would the derivative be if the radius doesn't change, meaning there is no dr dt in it, meaning that the radius is acting like a constant. But for the scenario that I have right now, the volume would change, so I would see dv dt in the rate of change equation. The height of it is not always necessarily going to be the same. I could have some height that's very little, maybe up about halfway, or up to the top. So the height might have some rate of change. So I'm going to be treating v like a variable. I'm going to be treating h like a variable. But I'm going to be treating r like a constant when I go to take the derivative of this function. Let's practice what the derivative of this function would look like then. So the formula is volume equals pi r squared h. And we just said that r is acting like a constant. Well, so is pi. So this right here is acting like a number would. And some of you might be thinking, oh, I know the derivative of a number is 0. Well, that's great if you want to be applying the product rule because you have two things being multiplied together. I can definitely find the derivative using the product rule, and if I do that, I am going to need to know that pi r squared's derivative is 0. But if pi r squared is acting like a constant, I also have the option to take the derivative using the constant rule. And that's what I'm going to do. I'm going to work on the derivative on the right side first. So this is a constant. The constant rule says you can just bring that constant down and then take the derivative of the piece that's actually changing. Well, I've taken the derivative of the right side. I definitely need the derivative of the left side. Here would be my derivative of the left side. So maybe I'm trying to solve for a dv dt if r is acting like a constant. If that's the case, here's my answer. But what if I have a slightly different scenario where I still have a cylinder, but for some reason the radius and the height are changing? So r is going to act like a variable. H is going to act like a variable because they're changing. That means they variate. But the volume is constant. So I have some cylinder, and maybe it's being pushed down or expanded in some way, where the volume of it is remaining the same, but the value for the radius and the height are changing. So I'm going to find the derivative where I treat v like a constant, r and h like variables. Well, I'll take the derivative of the left side. The derivative of the left side, if it's a constant, it's just going to be 0. Unfortunately, the derivative of the right side, I have two variables and they're being multiplied. I have a variety of ways to split this up. I'm going to choose to split it up where pi r squared is one piece being multiplied with h, and I'll apply the product rule to that. What I would like you to try right now is, can you apply the product rule to the right side? And even if you change the way that you decide to define if pi goes with h or pi goes with r squared, or pi is just going to be brought down later on, we should all have the same derivative. Pause this and then see if you get the same derivative that I do. Did you get all these pieces? Since it was the product rule, I took this aspect and I wrote it, and then I took h's derivative, that's dh dt, and then the product rule would say, all right, we'll now do the same thing where you have h and pi r squared's derivative. The derivative of pi r squared would be to bring down the 2, so 2 pi r, and then don't forget the chain rule would say, well, you also need the derivative of r. Well, that's going to be dr dt. So if I clean this up a little bit, it would really just be that our order might change, or perhaps I'm asking you a question of what does dh dt equal, or what does dr dt equal? If that were the case, then I would algebraically go through and I would solve the problem. If I have this one, there's really not a whole lot to do. Maybe you'd put the 2 before the pi, maybe you'd put the h before the r, or the h after the r. That doesn't really matter. It is common to have the dr dt or the d whatever dt at the end. This would be the rate of change if the volume was a constant, but the radius and the height actually changed. So now you're going to work on a worksheet, and the front of the worksheet will have the area formula for a circle, and you'll be told that the area is changing or it's not changing, meaning it's constant. You'll be told what it is you're trying to solve for in the derivative. Maybe you're trying to solve for dr dt instead of dA dt. On the back, you're going to have a very similar formula to the cylinder, except it's a cone, and so 1/3 comes into play there. And you're going to be given a variety of scenarios for that as well. I want you to work on this worksheet, compare your answers with other people. If for some reason you lose the worksheet or you don't have the worksheet, a blank one is also posted on our website so that you can work on those problems. And remember that next class period you will have a mini quiz, a couple questions on finding derivatives of formulas rather than of equations that we would graph. So our formula's derivatives will represent rates of change rather than slopes of tangent lines. All right, do the best that you can. Good luck.